Hi, welcome to Understanding Complex Exponentials, Lecture 9, Appendix, Derivation of Taylor Series for e to the x, sine of x, and cosine of x. In this lecture, we will derive the Taylor series for e to the x, sine of x, and cosine of x. Okay, so the Taylor series for a function f of x around the point x equals a is given by the following. F of x is equal to the sum over n from 0 to infinity of x minus a raised to the n power over n factorial times the nth derivative of f evaluated at a. So f of x is equal to f of a plus x minus a times f prime of a plus x minus a squared over 2 times f double prime of a, etc. And here a prime denotes a derivative. We will use this to get the Taylor series for the functions e to the x, sine of x, and cosine of x. Okay, let's start with e to the x. We will take the Taylor series formula and expand around a equals 0. So then we have that f of x is equal to the sum over n from 0 to infinity of x raised to the nth power over n factorial times the nth derivative of f evaluated at 0. We're interested in the case where f of x is equal to e to the x. We need the derivatives of this function evaluated at x equals 0. So first, let's get the 0th derivative of f evaluated at 0. Well, the 0th derivative of f is just the function f, so this is just f of 0. F of 0 is equal to e to the 0th power, which is just 1. Okay, next let's get the derivative d dx of e to the x. Well, d dx of e to the x is e to the x. Evaluating this at 0, we get e to the 0, which is 1. This also implies that further derivatives of e to the x evaluated at x equals 0 will be e to the 0, so they will all be 1. So we get that all of the derivatives evaluated at 0 that we have to plug into our Taylor series formula are equal to 1. Okay, so using our Taylor series formula with f of x equal to e to the x, we get that e to the x is equal to the sum over n from 0 to infinity of x to the n over n factorial times 1. We thus obtain the same series that we used in Lecture 3. So e to the x is equal to the sum over n from 0 to infinity of x to the n over n factorial. And this is equal to 1 plus x squared over 2 plus x cubed over 6, etc. Okay, next let's consider the Taylor series for sine of x. We will again begin by expanding the Taylor series around a equals 0. So again, f of x is equal to the sum over n from 0 to infinity of x to the n over n factorial times the nth derivative of f evaluated at 0. So we want to evaluate this for f of x equals sine of x. For the first term in the series, let's get the 0th derivative of f. So the 0th derivative of f evaluated at 0 is just equal to f of 0, and here f is the sine function, so that's the sine of 0, which is 0. Okay, Now, for the other terms, let's get some derivatives of sine of x. So the first derivative of sine of x with respect to x is equal to the cosine of x, and the first derivative of the cosine of x with respect to x is equal to the minus sine of x. Okay, so we have those two derivatives. From those two derivatives, we can derive the following. So, the first derivative of sine of x with respect to x, evaluated at 0, is the cosine of 0, which equals 1. The second derivative of sine of x with respect to x, evaluated at 0, is equal to the minus sine of 0, which is 0. The third derivative is equal to the minus cosine of x evaluated at 0, so that's minus 1, and the fourth derivative is equal to the sine, again evaluated at x equals 0, so that's 0. Now, further derivatives will be a repetition of these four. So, for f of x equal to sine of x, we have the following. The 0th derivative of f evaluated at 0 is equal to 0. The first derivative of f evaluated at 0 is 1. The second derivative is 0. The third derivative is minus 1. The fourth derivative is 0. The fifth derivative is 1. The sixth derivative is 0, etc. So we can see that the derivatives in the sum, where n is even, are all 0. So we only need the terms with odd n. We can keep only the odd values of n by writing n as 2m plus 1, where m is an integer. Then we sum over m instead of n from 0 to infinity. So this gives the following. We had that f of x is equal to the sum over n from 0 to infinity of x to the n over n factorial times the nth derivative of f evaluated at 0. Now for f of x equal to the sine of x, we get that the sine of x is equal to the sum over m from 0 to infinity of x to the 2m plus 1 power divided by 2m plus 1 factorial times f to the 2m plus 1 derivative evaluated at 0. Now we just need to put in the values for those derivatives. Okay, let's look again at the values of those derivatives. Remembering that n equals 2m plus 1, let's look at the cases of even m. So for m equals 0, which is the same as n equals 1, and for the case m equals 2, which is the same as n equals 5, the derivatives, so the first derivative and the fifth derivative, are both equal to 1. Okay, now consider odd m. For m equals 1, so that's the case where n equals 3, the derivative, so that's the third derivative, is equal to minus 1. So we can see that the derivatives take the values minus 1 to the m power. We thus get that the sine of x equals the sum over m from 0 to infinity of x to the 2m plus 1 power divided by 2m plus 1 factorial times the 2m plus 1 derivative of f evaluated at 0, which is just minus 1 to the m power. We thus get the relation used in Lecture 3. So the sine of theta is equal to the sum over m from 0 to infinity of minus 1 raised to the power of m times theta raised to the power of 2m plus 1 divided by 2m plus 1 factorial. And that's equal to theta plus minus theta cubed over 6 plus theta to the 5th over 120, etc. Okay, finally, let's use the same techniques to get the Taylor series for cosine of x. We again set a equal to 0. So again, we're starting with f of x equals the sum over n from 0 to infinity of x to the n over n factorial times the nth derivative of f evaluated at 0. We'll evaluate this for f of x equal to the cosine of x. First, let's get the 0th derivative for the first term in the series. So the 0th derivative of f, evaluated at 0, is just equal to f of 0, and in this case, f of x is cosine of x, so f of 0 is the cosine of 0, and that's 1. Okay, let's get the various derivatives of cosine of x. So the first derivative of cosine of x with respect to x, evaluated at 0, is equal to minus sine of 0, which is 0. The second derivative of cosine of x with respect to x, evaluated at 0, is minus the cosine of 0, which is minus 1. The third derivative is equal to the sine of 0, which is 0, and the fourth derivative is equal to the cosine of 0, which is 1. Just like before, these four values will repeat. So we get that the 0th derivative of f, evaluated at 0, is 1. The first derivative is 0. The second derivative is minus 1. The third derivative is 0. The fourth is 1. The fifth is 0. The sixth is minus 1, etc. Okay. So we had those values for the derivatives evaluated at 0. We can note that this time the odd derivatives are 0. So we can keep just the even terms by writing n as 2m and summing over m from 0 to infinity. So again, before we had f of x equal to the sum over n from 0 to infinity of x to the n over n factorial times the nth derivative of f evaluated at 0. For f of x equal to the cosine of x, we get that the cosine of x is equal to the sum over m from 0 to infinity of x raised to the power of 2m over 2m factorial times the 2mth derivative of f evaluated at 0. We can see that the derivatives evaluate to minus 1 for odd m. So for m equals 1, that's n equals 2, so we're looking at the second derivative. And for m equals 3, we're looking at n equals 6, so that would be the sixth derivative. So in those cases we get minus 1. And the derivatives evaluate to 1 for even m. So for m equals 0, that's n equals 0. We're talking about the 0th derivative. And for m equals 2, we're talking about n equals 4, so that's the fourth derivative. So both of those are 1. So what we get is that the 2mth derivative of f evaluated at 0 is equal to minus 1 to the mth power. So that tells us that cosine of x is equal to the sum over m from 0 to infinity of x raised to the power of 2m over 2m factorial times minus 1 raised to the power of m. And so we thus obtain the last of our 3 Taylor series expressions needed for lecture 3. So the cosine of theta is equal to the sum over m from 0 to infinity of minus 1 raised to the power of m times theta raised to the power of 2m over 2m factorial, which is equal to 1 plus minus theta squared over 2 plus theta to the 4th over 24, etc. We would encourage you to confirm that you can derive these expressions on your own.